Hello and welcome to this video all about finite element exterior calculus. This is the topic of my bachelor thesis, and I want to give you a broad overview on this topic since there are seemingly no approachable resources on this topic, even though it is actually very cool. It probably helps to have some familiarity with the finite element method, and it might even help if you've seen some concepts from differential geometry before. Let's get right into it. So you can think of finite element exterior calculus as being a marriage of the two theories of the finite element method and of exterior calculus. And really it just means that we want to formulate them using differential forms. So differential forms are the object at study in the exterior calculus. And FEEC, the shorthand for finite element exterior calculus, really tackles then the weak variational form of the PDE and tries to solve PDEs in this framework. Exterior calculus, what is this exactly? So really you can think of this as being a modern formulation of traditional vector calculus. And it is kind of calculus on Riemannian manifolds. So this is really rooted in differential geometry. And it unifies all the different kinds of integrals and derivatives you would find in vector calculus into basically just one object. And this generalizes then to arbitrary dimensions. Vector calculus sometimes is kind of limited to only 2 or 3 dimensions, since in high dimensions things like the curl doesn't work anymore. So what is a differential form? A differential K form is basically just an integrand, a K-dimensional integrand. For instance, we can have a one form living in the space of one forms, and it is basically just a line integrand, okay? You can integrate this over some curve. You can have a two form, which is an area integrand, which you can integrate over a surface. And you can have a free form, which is like a volume integrand, which you can integrate over a 3D patch of volume. And so a differential form then can just be integrated over a submanifold, and a differential K form can be integrated over a K-dimensional submanifold, okay? So you just write an integral sign and then the differential form directly comes, because it has the coefficients and these differential terms with respect to which you are integrating. And you can kind of think of these differential K forms as being K-dimensional rulers. And these rulers, they vary across the manifold according to these coefficient functions we've seen in blue. And at each point specifically, we have a fixed ruler which locally measures the tangential K vectors. And if we then do the whole integration, well, we globally measure the K-dimensional submanifold. So this is really a unified theory of integration for arbitrary dimensions. So after unifying integrals, we want to now unify derivatives. And there are really 3 central derivatives in vector calculus: the gradient, the curl, and the divergence. And they can all be written using basically just one derivative in exterior calculus, which is the exterior derivative. So these are unified. And if we now combine the unification of integrals and derivatives, we can even unify the main theorems from vector calculus, the gradient theorem, the curl theorem, the divergence theorem, into just one, which is Stokes' theorem, saying that the integral over a manifold of the exterior derivative of a differential form is the same thing as taking the integral over the original differential form over the boundary of the manifold. And now, how would one do now finite element exterior calculus? Well, we really just need to generalize them with these differential forms and formulate PDEs with differential forms. First of all, we need to recognize, since we're now in the space of differential geometry, we have a more general PDE domain. It can be any Riemannian manifold. And FEEC allows us to treat domains of full topological generality, meaning we can have arbitrary number of holes, which is usually referred to as arbitrary k-Betti numbers. So the k-Betti numbers measures the number of k-dimensional holes. So we can solve PDEs on the surface of a sphere, on various torus, and so on. And we need to somehow discretize this domain to now actually do the finite element method. And this is by means of a mesh. And really, usually one knows of these triangle meshes which discretize surfaces, but surfaces are just two-dimensional. We, of course, need to discretize arbitrary dimensional manifolds. So we make use of something called the simplicial complex. So a simplex is just basically a generalization of a triangle to arbitrary dimensions. So in 0 dimensions, you have just vertices. In 1D, you have edges. In 2D, you have triangles, as we know it. And in 3D, we have tetrahedron. And this you can extend this arbitrarily. You always have n plus 1 corners of a n-dimensional simple volume of a simplex. And the simplicial complex really contains all of these. So if we have a volume we're discretizing, we have tetrahedron, but in the simplicial complex we also have the faces of the tetrahedron, so the triangles, and these have, if you take the boundary of the faces, you get the edges, and if you take the boundary of the edges, you get the vertices. And all of these are in the simplicial complex, which is always connected by this boundary operator. And now, to motivate what FEEC really generalizes, we need to first look at them in vector calculus. And in traditional courses on numerical, on solving numerical partial differential equations, you usually treat only scalar valued PDEs in a Lagrangian finite element context. But one could also have vector valued PDEs, meaning the solution is a vector field. And a great example of this are Maxwell's equations, where we have an electric field and a magnetic field. And then we write the PDEs using these different operators. So in Lagrangian finite elements, you would usually use the gradient, since the gradient can be applied to a scalar function. And for vector fields, well, you apply the divergence and the curl. And in Lagrangian finite elements, you always formulate your variational problems on these function spaces, on these Sobolev spaces, of which the most common one is H1. The space of all scalar functions for which the gradient of the function is square integrable. But since we're now using also divergence and curl, we need Sobolev spaces for them. So how do they look like? Well, one could also call H1 just H grad, since this is the operator we are worried about. So we can also define H curl and H diff. Very easy. So this is the natural extension, and these spaces now include have as elements vector fields. And these spaces are actually very connected. There is this theory of the de Rham complex, which is this rich algebraic structure connecting H grad with H curl and H diff and eventually L2. And these are connected by their respective derivatives. So the image of H grad under the gradient operator, well, it is contained in H curl. And the image of H curl under curl is contained in H diff, and the image of H diff under diff is in L2. And that is not all. If we apply a differential operator twice, we always get 0. So if we were to start with the gradient and then apply the curl, we get 0. And if we first take the curl and then the divergence, we also get 0. This is because if the images of a differential operator are in the kernel of the next differential operator. And this is this interesting structure. And this structure is really important, and we will see it come up a couple of times. So we now need to devise finite element spaces as discretization of these Sobolev spaces. They just need to be finite dimensional subspaces of these infinite dimensional function spaces. And these have been meticulously constructed. The one you're probably already familiar with is the Lagrangian finite element space with the Lagrangian basis functions, the 10 functions, on the vertices of the mesh. And it is a subspace of H grad. There is a subspace of H curl, which is called the Nedelec space. And there is a subspace of H diff called the Ravier-Thomas space. And they also have basis elements, and these no longer live on the vertices, but the Nedelec live on the edges, and the Ravier-Thomas elements live on the faces of the mesh, interestingly. There is some underlying geometric structure here, and we'll see later on what it is. And in order to now get a good discretization of our Maxwell's equations, or any PDE, we need to respect the de Rham complex, because it really dictates the structure of the PDE problem. And only if we respect it in our discretization, we will get the right solution. We will converge to the actual solution. And this means we not only need subspaces, no, we need subcomplexes. And such a subcomplex is formed by these finite element spaces we found so far. So the Lagrangian finite element space is connected with the Nedelec finite element space, which is connected with the Ravier-Thomas space. And lastly, the L2 space becomes the piecewise constant discontinuous finite element space. And this is actually a subcomplex of the original one, which means, great, we have a good discretization. But for this, mathematicians needed to meticulously construct these spaces such that they fulfill this condition, which was kind of hard. And these spaces seem very separate, really. And this is because of vector calculus. Vector calculus makes a big distinction between these various sorts of derivatives. Exterior calculus doesn't. So can we achieve some unification here with exterior calculus? And can we maybe extend this to arbitrary dimensions? These differential operators from vector calculus, they really only work in 3D, maybe also in 2D and 1D, but in 4D it's really unclear what the curl should become. So let's look at what finite element exterior calculus does. So first of all, we need to rewrite Maxwell's equations such that they don't involve the derivatives from vector calculus, but they are written using differential forms. The electric field is a one form because, and this is actually dual to a vector field. A vector field is a line field, as is also a one form. It's one dimensional. So this is completely normal. But the magnetic field, interestingly enough, is a two form. So representing in vector calculus the magnetic field as a one form is actually not really the way to go. This is not true to its real nature. And being a two form, for instance, forbids magnetic monopoles, such as physics does. So this represents a more truthful representation of physics. And now we only have these four equations which only involve one derivative, which is the exterior derivative. And we can go even further and make use of differential geometry once again. We can formulate Maxwell's equations in relativistic electrodynamics, meaning we have these equations now on the 4D space-time manifold, treating arbitrary curvature of our 4D space-time due to gravity. And we can just define two things, the Faraday 2 form and the current free form, and we're only left with two equations. So this framework is already very interesting since it gives us a more natural way of expressing Maxwell's equations. But this is not all. Since we only have one kind of derivative, the exterior derivative, we really only need one kind of Sobolev space. The Sobolev space of all differential K forms for which their exterior derivative is square integrable. And this is a great unification. And furthermore, these are actually the same spaces as the grad, curl, and diff Sobolev space. They are isomorphic. So the zero forms correspond to the gradient space, the one forms to the curl space, and the two forms to the divergence space. So we already unified these. Only thing changing is the index up here, which differential K form it is. And actually, we therefore also get the same de Rham complex. It is isomorphic to it. But now it is a lot more streamlined. We always only increase the K in the differential K form, and all of the spaces are just connected by the exterior derivative. And this image being contained in the kernel of the next differential operator is now just the fact that the applying the exterior derivative twice is 0. So this is very simple. And now we can make a very, very interesting connection, which lies at the heart of finite element exterior calculus. Remember our simplicial complex. This simplicial complex connects the various manifolds, the various submanifolds of our original manifold through the boundary operator. So if we're in a three-dimensional space, we can take of any submanifold the boundary getting us a two-dimensional manifold, and then a one-dimensional manifold, and so on. And this also forms a complex, and it is connected by the boundary operator, which also twice application of it twice leads to 0. So this seems very, very similar. So why is that? Well, really, this is a very deep discovery on the connection between the topology of the mesh or the manifold and the calculus structure of our PDE problem. And this is called the connection between homology and cohomology. And if we respect this connection well, only then we can treat PD domains of arbitrary topological generality. And furthermore, not only do we have only one Sobolev space, we of course only have one kind of finite element space. The space of Whitney K-forms, which are differential forms which are piecewise linear over cells. Okay, so this is the most simple one, corresponding, for instance, to first-order Lagrangian finite elements. And the functions, the basis functions, live on the corresponding simplex of the same dimension. So if you have a differential K form, the basis functions live on the K simplices of the mesh. So this is here a connection between geometry and the differential structure. And this discretization of placing them there really respects this connection between homology and cohomology. So the Lagrangian finite elements are here the Whitney 0 forms, the Nedelec elements are the Whitney 1 forms, and the Raviat-Thomas are the Whitney 2 forms. And this explains why these live on the vertices, the edges, and the faces respectively, because they're the index of the geometry dimension, and the Whitney K form agree. And here again, we need to look for a subcomplex, and the Whitney K forms do form such a subcomplex, which has the same properties, giving rise to a good discretization. And there is even more. This is very asymmetric construction. We can extend this to arbitrary dimensions. You can just increase K on, and you can just connect these Sobolev spaces or Whitney K form spaces by the exterior derivative. So there's a very natural extensions to arbitrary dimensions here. And furthermore, as it is common in finite elements, there's not just piecewise linear approximations of PDE solutions. No, we can find arbitrarily polynomial degree solutions to our discretized PDEs. So we have these bases of piecewise polynomial differential forms for any degree R. So this is extremely general. So to recap, what is FEEC? Well, it is one thing for sure. It is extremely general. It supports arbitrary dimensions, arbitrary topological manifolds, arbitrary K-forms, and arbitrary polynomial degree finite element solutions. It is a theoretical framework, which is very math heavy, for establishing the well-posedness of PDE problems, and by respecting the co and homology. And this is basically one of the best theories probably for getting actually devising methods that actually converge to the right solutions of PDEs. And lastly, it is not only a theoretical framework, but it's a manual for creating a FEM library of the same generality as FEEC. And this is now exactly my bachelor thesis. I'm trying to write a Rust implementation of finite element exterior calculus on coordinate-free simplicial manifolds. And this is what I'll be working on. And I hope to create some more videos on these topics, especially with regards to how to implement this. Thank you so much for watching. If you want to find the slides, which are written in types, this new language, this new typesetting language, which is might be the successor to LaTeX, you can find them on GitHub. And if you want to take a look at my Rust FEEC library, you can also find it on GitHub. Thank you for listening, and goodbye.